All right, let's talk about one of the most powerful tools in all of computer science, the hash table. Its promise is simple, but honestly, it's incredible. We're talking about the ability to find, add, or get rid of data almost instantly. So let's dive in and see how they pull off this magic trick.
Okay, so just imagine for a second, you're scrolling through millions of contacts in your phone, or you're on a massive online store with millions of products. How do you find that one specific thing you're looking for in the blink of an eye? How is that even possible? Well, this is the exact problem that hash tables were born to solve.
Now this is where it gets really interesting. Look at that performance leap. Searching an array, that's ON, is like looking for a book by literally checking every single book on every shelf one by one. A binary tree, or O-log-N, is way smarter. That's like having a guide that tells you which aisle the book is in. But a hash table, O1, that's like having a magical GPS that just teleports you directly to the exact spot where your book is sitting. It's a total game changer.
So what is this thing really? At its heart, a hash table is just a collection of key-value pairs. The best way to think about it is like a dictionary. You got a word, that's your key, and you have its definition, that's the value. A hash table is just a super optimized way to find that definition instantly just by knowing the word.
The real magic happens in this beautifully simple process. You take your key, let's say it's username, and you feed it into a special hash function. This function is like a super fast sorting hat. It doesn't think, it just does a quick calculation and instantly spits out a number. That number is the index, or the exact slot where your data lives. That's it. No more searching, just pure direct access.
Now here's the crucial part. The entire system, all of its incredible speed, it all hangs on the quality of that hash function. A good one has to be deterministic, meaning the same key always gives you the same index. No exceptions. It has to be super fast. It needs to spread the data out evenly, not clump it all together. And most importantly, it has to be really, really good at minimizing a huge problem we're about to get into.
And here it is, the #1 challenge, the main villain in the world of hash tables, the collision. This is what happens when your hash function takes two completely different keys, but assigns them to the exact same spot. Now you've got two pieces of data trying to sit in the same chair. So what do?
Okay, let's make this crystal clear with a simple example. You know, the kind a professor would definitely put on an exam. Let's say our hash function is just k mod 10. It takes a number and gives us the remainder after dividing by 10. So what happens with the keys 15 and 25? Go ahead, pause the explainer, and see if you can figure it out yourself.
All right, you back? Let's take the first key, 15. We run it through the function 15 modulo 10. The remainder is 5. So our hash function tells us to put the data for key 15 into slot number 5. Easy enough, right?
And now for key 25, we do the exact same thing, 25 modulo 10, and the remainder is also 5. And there you have it. Two different keys are trying to get into the exact same index. That, my friends, is a collision.
So, if collisions are basically inevitable, how on earth do we fix them? Well, luckily for us, programmers have come up with a couple of clever strategies to handle this. Let's check them out.
Okay, so on one side we have what's called chaining. With this method, you can think of each slot in the table as a little hook. If two items are supposed to go in the same slot, no problem. We just hang the second item on a chain hanging off that hook. The other main approach is open addressing. This one is more like finding a parking spot. If your assigned spot is taken, you just drive down the row and take the next empty one you find. Both are great solutions, and they each have their own pros and cons.
Now, within open addressing, there are a few different ways to find that next empty spot. Linear probing is the most basic. Just check the very next slot, then the next one, and so on. Quadratic probing tries to avoid bunching things up by taking bigger and bigger jumps. And then there's double hashing, which uses a whole second hash function just to figure out how far to jump. It's often the best at spreading things out.
Now this right here is a really subtle but super important detail. With open addressing, you can't just delete an item and leave an empty hole. I actually learned this the hard way on a project. I deleted an item and suddenly my search function broke for a bunch of other items. It took me forever to realize that the empty slot I created was acting like a dead end in the search path. The solution is to use a special marker that basically says, hey, something used to be here but it's gone now, so just keep on searching past me.
And this brings us right back to performance. Just look at this table. The average case for everything we want to do is that beautiful, magical, instant O1. But take a look at the worst case column. It's ON, the same as a slow, simple array. This nightmare scenario happens if you have a terrible hash function and everything collides into one long, messy chain.
This is the million-dollar question, isn't it? If O of 1 is the dream and O of n is the nightmare, what's the key factor that keeps us living the dream?
Well, the answer comes down to one simple metric, the load factor. It's just a ratio, the number of things you've stored divided by the total number of slots available. Let's go back to that parking lot analogy. The load factor just tells you how full the lot is. Is it 10% full or 90% full? It's a critical health metric for our hash table.
So, what if our load factor starts getting really high? Let's say it hits 0.9. This means our hash table is 90% full, and right about now, some serious alarm bells should be going off in your head.
A high load factor is a huge red flag. When the table is almost full, the chance of a collision just skyrockets. Think about it. When the parking lot is almost full, finding an empty spot becomes a huge pain, right? It's the same thing here. Your performance starts to crawl, getting closer and closer to that O(n) worst case.
To prevent this performance meltdown, hash tables have a built-in safety net called rehashing. As soon as the load factor hits a certain limit, usually around 70%, the system automatically says, "Whoa, we're getting too crowded." It then builds a brand new, much bigger table and carefully moves every single item from the old table into the new one. It's like moving into a bigger house when your family grows, and it's what keeps performance lightning fast.
So where do you find these things in the real world? The short answer is literally everywhere. That dictionary you use in Python or the hash map in Java? Yep, those are hash tables. Databases use them constantly for indexing to find data quickly. Caching systems depend on them. They are one of the absolute fundamental building blocks of almost all modern software.
All right, let's bring it all home. After all that, what are the most important things you need to walk away with?
First, they are built for speed. For lookups, insertions, and deletions, they're one of the fastest things we have. Second, the hash function is everything. A good function means good performance, a bad one means disaster. And third, collisions are going to happen. The most important part of building a good hash table is having a smart strategy to deal with them.
And I'll leave you with this last thing to think about. We've seen how amazing hash tables are for speed, but that hashing process, it completely scrambles any natural order the data might have. So what if you needed to pull out your data in alphabetical or numerical order? Would a hash table work? The answer is no, it wouldn't. And that's maybe the biggest lesson of all. There's no single best data structure. The real art is understanding the trade-offs and choosing the right tool for the job. Thanks for watching.